We're going to do number 1 from this homework set. So you can read it off your paper. Alright, let's go through the steps. So, number 1, we need a drawing of what's going on. So we have a missile going up. Okay, so it's 75,000 feet from a radar station. It's going up at some angle, and then we don't know this Y value here. Okay, so we've got our drawing. Since it's rising 16,500 feet, that's a rate for dy over dt. So let's start filling out our rates over here. So we know that dy over dt, so that's how much it's going up in terms of time, is 16,500 feet per minute. Okay, and then they're asking us to solve for the change in the angle of elevation. So A stands for angle of elevation in time. So we're looking for what that is when y is 38,000 feet. Okay, so we're not plugging in y here as 38,000 because that missile keeps going up. So this number is going to be changing. So we're going to plug this in later. We're not going to plug it in yet. Okay, so now we need an equation. Okay, so we need an equation for an angle, which means we're going to be doing trig. We have a right angle, so we have sine, cosine, tangent. If we have a y and then this x value here, we're going to do tangent, because tangent's opposite over adjacent. So tan of A is equal to opposite, which is y, over the x value here, 75,000. Okay, now we need to differentiate. Okay, this is where you have to remember your derivative rules. So the derivative of tan is secant squared of A times the derivative of A with respect to time, and that's equal to the derivative of this side, which is 1 over 75,000 times dr over dt. That's wrong. That should be dy over dt right there. Okay. Alright, now we need to start substituting and solving. So let's see what information we have and if there's anything else that we need to find. So we don't know what A is. We also don't know what dA over dt is because that's what we're trying to solve for. We do know what dy over dt is because that's right there. So we need to find A when x is 75,000 and when y is 38,000. So in order to do that, we're going to use the same equation. So tan of A equals, but this time we're going to say y is 38,000 and x is still 75,000. Alright? So basically on your calculator, you're going to do inverse tan negative 1 of 38,000 over 75,000. That's how you solve that. And that'll give you A. So if you do that, you'll get approximately 0.469. You want to save more numbers in your calculator when you do that. So when you come back and plug it in, you get a more accurate answer. Okay? So now we're ready to substitute, so I'm going to do that over here. So we're going back to our derivative. So remember, secant squared means secant of A squared. So we have secant of A, 0.469, whatever other decimals, squared. We don't know dA over dt, equals 1 over 75,000, and then dy over dt is 16,500. Run out of room over there. Okay, so now we're ready to solve. So in our calculator, we're going to type in secant. Actually, that's not on our calculator, so you guys have to remember secant is 1 over cosine 0.469. Then you'll square that. That value right there is, I don't know, I just figured out what it was and went from there. So then you have dA over dt equals 16,500 over 75,000. So basically you're going to figure out what this value is, divide both sides by it, and you're going to get dA over dt is equal to approximately 0.175. And our units on this, the units for our angle, that's not area, that's angle, is radians per minute. Okay? So what we're saying is that the missile's angle of elevation is increasing at a rate of approximately 0.175 radians per minute.